In this video, we will be solving this JEE 2017 question, which is about a rocket launch. Let's read this question first. A rocket is launched normal to the surface of the earth, which means if this is the earth, it is launched normal to the surface of the earth. The sun, away from the sun, along the line joining the sun and the earth, along the line joining sun and the earth. So maybe it's something like this. This is the sun and the line joining this, and the rocket is launched in upward direction. The sun is 3 into 10 to the power of 5 times heavier than the earth and is at distance of 2.5 into 10 to the power of 4 times larger than the radius of the earth. So for now, let's keep this info in the side and let's go forward. The escape velocity from Earth's gravitational field is VE is equals to 11.2 kilometer per second. Okay, fine. The minimum initial velocity Vs required for a rocket to be able to leave the Sun-Earth system is closest to is the question, and we have gotten some options. Vs is equal to 22 km per second, which is nothing but system velocity of the system, escape velocity of the system of Earth, Sun, and also the rocket. What is the escape velocity of the rocket to escape from Earth Sun system? So we have got few options here. So to understand this, we have to understand what is gravitational potential energy. So if I switch this, or I'll take a new paper. Imagine if we have two balls, any balls for that matter, in the deep space, which means no other object or mass is influencing their forces or their movement or them. So only this ball 1 is having an influence of gravitation on this. Also ignore all the other forces, electromagnetic, weak, nuclear, or radioactive, whatever forces they have. Just keep this a deep space, and only gravitation of these two balls is acting on each other. This is ball 1 and probably ball 2. And the force we have is given by Newton's gravitational law, G(m) by r square. What is force is, because it's gravity, they both are pulling each other. So because they are in deep space, they will eventually collapse into each other. Eventually, because they are in deep space. But this may not happen on the earth or in general circumstances, because we have other forces acting on them. For example, if we take the example of the earth and the moon will never fall on the earth because it also has some tangential acceleration, tangential velocity. But in deep space, when the two objects are stationary, they will eventually collide with each other. So this is what we call as force, gravitational force. But at a particular point in time, this system of balls will have a gravitational potential energy, which is given by G(m) by r. This is the only difference that we have, r square and the r, which means, for example, if we have these two bodies at some time 1 second probably, and now this same bodies at 2 and at 3, all these scenarios, the graph of potential energy to time is linear. It's, as time decreases, it's increasing, right? So it's linear. But for force is little different. At this instance, force is actually increasing. It has exponential curve. So now to solve this, what we have to do is, I'll just take another page, I guess. if we take this rocket and we have the sun somewhere, something like this, the potential energy of this system of Earth and the rocket is GME m by r square. R square is actually the radius of the Earth, so RE square. But now also, if we ignore the Earth and we have the sun here, the potential energy of this system is m is actually the mass of the rocket. This is the mass of this rocket. This is also the mass of the rocket, and we have r square, but here r is the distance between the sun and the rocket. So this, we have this too. Now what we have to understand is the initial kinetic energy of the rocket, which is this kinetic energy, which is half mv square, should be equal to GME m by r square of Earth. First, this system's potential energy plus this system's potential energy, which is GMSM by r square s to rocket. Here this velocity mv square is of system, m of system. So what we have to find out is actually this mv square of a system. So basically, by doing some simple maths, mv square of system is equal to 2gmem by re square plus 2gmsm by r square s to r. We get m will get cancelled, so we get v square of system will be equal to 2gme by re square plus 2gms by r square s to r. Now this is nothing but escape velocity square of Earth. I'll write ESP. This is for, by default it's for Earth, will be equal to 2gme re square. Sorry, it's just re, right? This re. This is re. Sorry. I got this wrong. It's just re plus this is this. So we'll substitute it. Take another page. I don't know. So we have v square of system is equal to v escape square plus 2g m of sm divided by r s to r, what we have. Now because they have given this and this with respect to Earth's mass and Earth's radius in the question, so we have it here. Which is actually 3 into 10 to the power of 5 times heavier than Earth, which means, this is our paper, man, which means 2g ms can be written as 3 into 10 to the power of 5 into me into m divided by rs square is also given as 2.54 times, which means 2.5 into 10 to the power of 4 into re. Now if we take 3 into 10 to the power of 5, 2.5 into 10 to the power of 4, and then 2gme into m by re. This is nothing but again ve square, escape velocity. And if we do this calculation, this goes to VE square plus, if I do this, this is also VE square is equal to V square SYS system. So if we substitute, if you can see, 3 into 10 to the power of 5 divided by 2.5 into 10 to the power of 4, we get the answer as 12. If you can see, it's 12. So it's basically 12 VE square, which is nothing but 13 VE square. V square is SYS system, and removing the squares we get root 13 VE, and root 13 into VE. VE is also given in the question, which is 11.2 kilometers per second. So root 13 into 11.2 or 13 into which is equal to 40.382 kilometers per second. And the closest answer we have to this is A is too small. This is the closest I think we get. 62, 72 is too large. So this is approximately equal to 42 kilometers per second. So this is the answer, which is B. But there are many other ways, which is option B, but I think there are 2-3 other conceptual ideas that we can use to derive this, to solve this. The first one was of this potential energy thing, so which is of GM by R. But now if we imagine, if you take sun, something like this, and earth and rocket as one thing, and now we have to shoot this earth out of this orbiting velocity. If you know already, the orbiting velocity of earth is 30 kilometers per second, and to shoot out an orbit, we have, if you want to escape from an orbit, the escape velocity of the earth into root 2, which is escaping the orbital or escaping in orbit, then you get around 42 kilometers per second. So I will show you once, which is 30 into root 2, we will get 42.42 kilometers per second. There is another way to do it. Actually, if you add Earth's gravitational force, it gets little bigger, which will get around 4.4344. I don't know what it is, but the closest that we get is again 42 from our questions, is 42 kilometers per second. (42 kilometers per second).